Now that we have learned chemical shift, integration, splitting, and degree of unsaturation, let's put everything together. In this video, we will interpret proton NMR spectra step by step and deduce the structure. In many exam questions, proton NMR is not used alone. Proton NMR alone may not be enough. We are usually given the molecular formula, proton NMR spectrum, and pick data such as chemical shift, integration, and splitting. The formula gives us the atoms present, while the spectrum tells us how those atoms may be arranged. A good method is to start with the molecular formula and calculate degree of unsaturation. Then count the signals. Read the integration, interpret the splitting, use the chemical shift, assemble fragments, and check that the final structure fits all the evidence. So, do not use one clue alone. For the teaching examples, I may display spectra at 100 MHz, so the splitting patterns are easier to see. In real NMR work, higher frequency instruments such as 400 or 600 MHz are often preferred for better resolution. The chemical shift values in ppm remain essentially the same. ppm chemical shift stays essentially the same, regardless of the spectrometer frequency, but splitting can appear more compressed on the ppm scale at higher frequency. Let's start with a compound with molecular formula C₄H₈O₂. The proton NMR data shows 3 signals: a 3-hydrogen triplet near 1.2 ppm, a 3-hydrogen singlet near 2.0 ppm, and a 2-hydrogen quartet near 4.1 ppm. We want to deduce the structure. First, calculate degree of unsaturation. Oxygen is inert. Du equals 4 carbon minus 8 hydrogen over 2 plus 1, which gives 1. So the molecule has 1 ring or 1 pi bond. Since the formula contains 2 oxygens, a carbonyl containing compound is possible. Now, let's look at the spectrum. There are 3 signals. 1, 2, 3. So, there are 3 proton environments. The integration is 3 hydrogens, 3 hydrogens, and 2 hydrogens, giving a total of 8 hydrogens. This matches the molecular formula. A 3-hydrogen triplet together with a 2-hydrogen quartet is a classic ethyl group. The CH₃ group is split by the neighboring CH2, giving a triplet because of the n+1 rule. 2 plus 1 equals to 3. So, a triplet or multiplicity equals to 3. The CH2 group is split by the neighboring CH3, giving a quartet because of 3 plus 1 equals to 4. Multiplicity equals to 4. So, we likely have a CH2-CH3 fragment. The 2-hydrogen quartet appears around 4.1 ppm. This is quite downfield for an ordinary alkyl CH2. So it suggests that the CH2 is attached to a highly electronegative oxygen atom. Therefore, the ethyl group is likely OCH2CH3. That's because CH2 near oxygen is more de-shielded. The 3-hydrogen singlet near 2.0 ppm suggests a methyl group next to a carbonyl group. It is a singlet because the adjacent carbonyl group has no hydrogen atoms attached to it. So this suggests a CH₃CO group, where the CH3 is next to a carbonyl group. We now have found 2 fragments, CH₃CO and OCH2CH3. Combining them together gives CH₃COO CH₃CHCH₃, which is ethyl ethanoate. This structure fits the formula C₄H₈O₂. Degree of unsaturation equals to 1 because of the carbonyl group, integration, splitting, and chemical shift. Now, let's try a second example. The molecular formula is C₃H₃Br. The proton NMR data shows a 6-hydrogen doublet and a 1-hydrogen septet. Doublet refers to a multiplicity equals to 2, while a septet refers to a multiplicity equals to 7. Let's deduce the structure. For degree of unsaturation, bromine counts as 1 hydrogen. So C₃H₃Br is treated as C₃H₈. Du equals 3 carbon minus 8 hydrogen over 2 plus 1, which gives 0. So there is no ring and no pi bond. The spectra has 2 signals, 1, 2. So there are 2 proton environments. The integration ratio is 6:1. A 6-hydrogen signal suggests 2 equivalent CH₃ groups. The 1-hydrogen signal suggests 1 CH proton. The 6-hydrogen doublet suggests 2 equivalent CH₃ groups. Each CH₃ group is next to 1 neighboring hydrogen. So, using the n+1 rule, 1 plus 1 gives 2 lines, which is why the CH₃ signal is a doublet. The 1-hydrogen signal is a septet. A septet means 7 lines, or multiplicity equals to 7. So the proton responsible for this signal has 6 equivalent neighboring hydrogens. This fits a central CH proton next to 2 equivalent CH₃ groups. The 1-hydrogen signal appears fairly downfield because that proton is on a carbon attached to bromine. Bromine is electronegative, so the CH₃Br proton is de-shielded. The structure that fits is CH₃CHBrCH₃, which is 2-bromopropane. The 2 CH₃ groups are equivalent and gives 6-hydrogen doublet. The central CH proton gives the 1-hydrogen septet. Why is this spectrum not 1-bromopropane? 1-bromopropane would have 3 different proton environments, not just 2 signals as what we see over here, 1, 2. The 2 signal pattern points to a more symmetrical structure, which is 2-bromopropane, and that rules out 1-bromopropane. To interpret proton NMR properly, combine all the clues. The formula tells us the atoms present. Du tells us rings or pi bonds. The number of signals gives proton environments. Integration gives the number of hydrogens. Splitting gives neighboring hydrogens. Chemical shift tells us the type of environment. The final structure must fit all of them. Structure must fit all clues. In the next video, we can look at labile protons and D2O shake. Why OH and NH peaks can behave differently in proton NMR. If you want to learn more about A-level chemistry, be sure to subscribe to this channel, and I will see you in the next one.